Hello everyone. Welcome to the lecture 14. In lecture 14, we're going to talk about the preloading with vertical drains. In lecture 13, in previous class, we've seen how to design the preloading when you don't apply the vertical drains. So continuing from the lecture 13, we're going to test and explore how to design the preloading with vertical drains. So the learning objectives are to understand the installation of vertical drains to accelerate the consolidation rate. So typically the vertical drains are applied to speed up the settlement. So when you remember the T2, what the T2 is, the T2 is the time at which that surcharge load is removed and the time that you begin to build the real structure. So then if the T2 is too long, then it's gonna cost a lot of money and also resources. So you wanna minimize the T2, the time that you have to wait until the settlement occurs to the amount that you wish to or desire. So the vertical drains are to shorten that kind of a waiting time for the settlement to occur. And the second objective is to describe the radial flow induced consolidation. So when you apply the vertical drains in the clay layer, it's add up the water before, without the vertical drains, the water flow only vertically. Right? So it's gonna be squeezed out to the top layer and the bottom layer, or just one of them. Right? But as soon as you install some drainage paths, then the water will flow in radial direction to the drainage pipe, and then it will just flow and drain out. So, and the third is to compute the degree of consolidation due to the vertical and horizontal drainage using Barron's equation. So the last objective is to be able to compute the degree of consolidation considering this radial direction drainage and the vertical direction drainage. So let's move on. As we talked before, the clay has very low permeability, so that it causes the slow rate of consolidation. So in this case, we use vertical drains to accelerate the drains and to faster the consolidation. So here it shows some typical section view of the vertical drainage, the site. So this is the earth field. And you apply is a drill and install, and the backfill this kind of the column, sand column in the clay layer or the silty clay layer or some fine grained soil. So the installation of this kind of vertical drainage induces the horizontal drainage or the radial direction flow. So this only affects the rate of settlement. So it does not alter the ultimate settlement as we talked before. So then the spacing between this drainage hole or the drainage column will be very important. That will be the core design parameters in this kind of application. So coefficient of the consolidation in horizontal direction or say the radial direction is important. Commonly, so in the horizontal direction, when you use the horizontal, then we use the CH, C sub H. Or if you think that is a radial direction, then CR can be also used. And CV, so when the coefficient of consolidation for only the vertical drainage, use the CV. So commonly the CH over CV is 1 to 2. So which means that the CH is larger than the CV typically. So the horizontal direction coefficient of consolidation is larger than the vertical direction coefficient of consolidation. I think this is related to the fabric of the clay. Traditional method of the installation is to derive the boreholes through the compressible soil layer and backfill with the suitably graded sand. So this graded sand should have high permeability so that it can, in this kind of a soil, the water can flow easily. The typical diameter of this borehole is about 20 centimeter to 40 centimeter. So that's about this much of size, or it can be this big size. Sometimes you can install some sand column up to 50 centimeter. Now, sand drains should be efficient for drainage, not allow migration of fines. Recently, prefabricated drains, or referred to as rig drains made of woven polypropylene filled with sand are used. This has some advantages because it's flexible, and because it's prefabricated, you can use some big diameter of. The typical diameter, no, it's not big. Typical diameter is about 6.5 centimeters, so it's less than the sand drains. But it can be used up to the depths of 60 to 90 meters. But in the sand drains, the typical depth is up to 30 meters. But in both installation, whether you use the prefabricated drains or sand drains, always there are some problems with the smear zones, because when you drill it, you're disturbing the soil at the wall, the drill hole. And when you replace and backfill the hole, this empty hole, with soil or the sand, then it can mix a little bit. And with the flow, also the fines migrates to the sand drain, so that with this flow, it brings some fine particle and get clogged in this sand drain, so which reduce the drainage rate. The smear zone is the thickness of the smear zone is also the important parameter of the factors affecting these vertical drains. Commonly, the common patterns of the spacing or the common patterns of vertical drains are the square pattern or the triangular pattern. So in square pattern, the drains are placed at regular spacing in a square pattern. And here the spacing is called the S, the capital S. And the influence radius, or the R, here is 0.564 times S. And here the R, the small RD, is the radius of the sand drains. In triangular pattern, so the effective area is kind of hexagonal. So the spacing here is in triangular pattern, also the S and S here. And the R, the influence radius, will be 0.525 times S. Okay, then how to analyze this vertical drain, the consolidation with the vertical drains? So the question will be, maybe we have already the given T2. For example, without the vertical drains, it's gonna take maybe 2 years for time factor or for the T2, so to be removed, for the surcharge loading to be removed. Then contractor said the 2 years is too long, so we had to reduce it to maybe like 3 months. So then T2 is given as 3 months. Then also the delta PF and the delta PP is given, because we know what kind of structure will be built. So then what will be the spacing? So we can design the spacing, the R value. So for example, for a certain area, we have to install the drainage pipe or send the drains like at maybe 1 meter interval, 1 meter distance, or every 1 meter, or every like 3 meter, or every 5 meter. That kind of a decision can be made if you do some analysis that we're gonna cover here. So for a given t, you can you can design the R, or if the R is given, then you can predict the T2 where the surcharge settlement is completed. So let's assume that the RD is the radius of the sand drain, so the diameter will be 2 times RD, and the D is the clay layer thickness, and 2R is the diameter of inference range between these the drains. So when the vertical flow occurs only, the Tae-Hyuk's one-dimensional consolidation theory is valid. So round U over round T equals CV times round squared U over second derivative, partial round U square over round Z square. So then we can get the solution for this equation, and this U is the accessible pressure at the given Z depth and at the given time of interest. So when the vertical and radial flow occurs at the same time, then we have to use the cylindrical coordinate. So then instead of Z, just depth, we can now use the R and Z and the time T. So round U over round T is CH, the horizontal direction coefficient of consolidation, and round U square over round R square plus 1 over R, round U over round R, plus CV, and this is for the vertical component, G square. So as you can see that in addition to the vertical component, vertical drainage, you have a radial drainage. So this component, a horizontal flow. So solution to this equation can be written in 2 parts. So first part is a drainage in the vertical direction only, and the second part is for the horizontal direction only. So you're gonna derive the U for this part first, and then this part later. So vertical part is the same, just the same, or exactly the same to the one-dimensional Tae-Hyuk's consolidation theory. So the average degree of consolidation due to the vertical drainage UV is function of time factor TV. And here time factor TV is the time factor for the vertical drainage. TV is CV times T over HDR squared. So if the TV is x-axis and the UV is the y-axis, then it's gonna increase like this, as we saw this graphic for in the handout. So T and UAVG, and so as time factor increases, average degree of consolidation also increases. So then you can approximate this curve to 2 simple equations. So when the time factor is larger than 60, the average degree of consolidation is larger than 60, you can linearize this curve with this linear equation in a log scale. And when the degree of consolidation is less than 60, then it can be also linearized with this square root of t. So I hope you remember this equation as you approximate this curve, for UAVG less than 60%, time factor for the vertical drainage is pi over 4 UV square. And when UAVG is larger than 60%, time factor is 1.781 minus 0.933 log 100 minus UAVG. So once TV or time factor is known, then average degree of consolidation can be estimated. So then, again, from that you can calculate the this U value is appropriate for the design value R or not. You can check for that. But that's for the only vertical component. We have to consider the degree of consolidation completed by radial, also accelerated by the horizontal drainage. So the second is the radial drainage part, and the solution is derived by this Baron in 1948. And here the UR is also a function of TR, so time factor in radial direction. So, and the TR is CH times T over 4R squared. Here the R is the influence range, right, between the spacing. So we know that the R is function of the spacing between the drains. So I think in previous pages here, the R is 0.564 times S for the square pattern, and for a triangle pattern also we have this equation. So closure spacing, as the S decreases, you have R decreases, then you have high TR and high UR, so it's gonna give you the faster consolidation. So according to the Baron equation, UR is 1 minus exponential function of minus pi minus 8 times TR over alpha. And here the alpha is n squared over n squared minus 1 natural log of n minus 3 n squared minus 1 over 4 n squared. And also the n has not been defined. So n is r over small rd. And here the r is the equivalent radius, and small rd is the radius of the vertical drains. So, and you can use this equation, and also you can use this equation for a given TR and for a given N. So you can estimate the UR using this chart from the handout. So then UR is from the degree of consolidation by the radial or the horizontal drainage, and the UV that we derived in the previous page here. This is the UV. UV is the degree of consolidation due to the vertical drainage. So then how can we combine these two? So we are interested in combined the vertical and radial average degree of consolidation. So Kallio also suggested that you can get the combined degree of consolidation by multiplying UV, 1 minus UV times 1 minus UR. So using this, you're gonna get this representative average degree of consolidation. Then you can check the design value R, the spacing, or the time T2 proper or not. So the one thing that you have to know is that we are using UAVG, not UG at the center. Why? Because there's a vertical drains like this, so that water can flow horizontally evenly along the depth. So there's no this kind of distribution for this, the radial direction degree of consolidation. So no more the using this conservative value is necessary. So we can just use the UAVG as we derived before. Okay. So in this lecture, we've seen the vertical drains and the radial flow consolidation and how to compute the degree of consolidation considering the vertical and the horizontal drainage using Barron's equation. Okay, so in the class, we're gonna practice with the examples how to use these equations to design or to check the design value for the vertical drains in the surcharge loading.